We're going to make an attempt. So it's my pleasure to welcome you to the second session of Featured Talks at CyberSEED 2017. I'm Ben Fuller. I'm going to be talking later, so you'll hear a little bit more about me. We have 4 great talks lined up. The first one is Brian Malacchia from Microsoft Research. He's the head of the crypto and security group. He's been there since,
20 years.
Yeah, I was going to say at least 2000, right?
97.
Before that, spent some time at Bell Labs. He has his bachelor's, master's, and doctorate from MIT. The current focus of the group is in post-quantum cryptography, which he's going to talk about today. So can everybody join me in introducing Brian? Thanks. Sure.
Okay, there we go. All right, so thank you, everyone. Thank you, Ben. Again, my name is Brian Malacchia. I run the security and crypto group at Microsoft Research. I have the coveted right after lunch slot. Everybody's now had a nice big meal. They're coming back. You're sated. You need to be woken up. And now I'm going to tell you about the coming cryptopocalypse and how we're going to lose all our public key algorithms. So nice cheery talk for right after lunch. Let me begin by talking a little bit about history and to kind of give you some context for the whole problem space we're talking about here. If you think about it, we've actually, as a species, been computing for over 2,000 years. We started with mechanical devices to calculate astronomical ephemera, such as the Antikythera mechanism, which dates back to 100 BC. We built or specified at least other types of mechanical computation, such as Babbage's difference engine, which was designed but never built. We had a transition to electronic computers, starting with things like the ENIAC in the late 40s, up through current supercomputers like the Tianhe 2, which is, for a few years, was at the top of the top 500 supercomputing list. And now we're on the cusp of another change in the underlying physics of our computer systems, or at least adding a new type of computer to the mix, those based on quantum mechanical properties, such as topological quantum computing, which is what the quantum computing group at Microsoft Research is working on, and there are many other types of underlying physics for building quantum bits or qubits that researchers around the world are working on. None of these scale yet. I'm not going to tell you that today somebody's got a quantum computer of any reasonable size that could do anything significant. If they can factor 15, that's good, okay, as far as these things go. But they're coming, and it has significant positive implications for new classes of problems that are currently intractable that we're going to be able to solve in things like metallurgy and chemistry and weather prediction and some physical systems, but it's also going to have a potential downside too. And understand this, if you look at the success of digital computers, we all know what Moore's law is. We all know that roughly every 18 months the computing power doubles. And here I've got a log scale on the left, and so I get a nice linear plot of the number of megaflops or teraflops per second over time. And that green line is the sum of all the computers in the top 500 supercomputer list, and then the kind of orangish one is the top element, and the blue is the bottom of the top 500 list, and everything seems to follow that nice trend. And so what you normally do is you ask the question, well, what are the things that you can't solve with digital computers? What are the sorts of problems where I can't just wait for Moore's law to take care of it? I can't just go order more racks of machines or go, just assume that compute power is going to double. Well, here's the one I care about, or an example of what I care about, RSA, factoring. Right? The difficulty of factoring large numbers is the underlying number theoretical problem that the RSA algorithm is based on, and it's an intractable problem for classical computing at the sizes that we use today to protect everything on the internet. This is the 2048-bit RSA challenge problem. That's a number that's the product of two 1024-bit primes. If I gave any of you the two 1024-bit primes and I said multiply them, it might take you a little while to do it, but even with pencil and paper, you go multiply that out. If I ask you to go factor that, go in reverse, we can't do it until the heat death of the universe, basically. Billion years, billion CPU years is what it'll take to factor that with best known factoring algorithms. But if I got a quantum computer, I can do it in 100 seconds. Now that's not a new result. That's actually a result that goes all the way back to Peter Shor in 1994 at AT&T Bell Labs when he came up with the first quantum factoring algorithm for a computer that no one thought would exist, or at least not in any reasonable amount of time. Well, now it's starting to look like it might exist in a reasonable amount of time. More precisely, if you look at the work factor curves associated with something like breaking RSA, the curves on the left are what we could do in terms of number of bits across the horizontal axis and how long it takes on a log scale on the vertical axis. And our best factoring algorithms are sub-exponential, but they're super polynomial. They're sub-exponential growth. And so if we think that the amount of compute power that an attacker might be able to bring to bear on a factoring challenge is getting anywhere close to viable, we can increase the number of bits in the key by a few and gain the benefits of that sub-exponential curve and drive the work way up. And between 2003 and 2018, that curve hasn't changed much. It's shifted a little bit, but that's basically it. Quantum brings a different type of curve, or a line in this case, to the table, where if I want to attack a number, an n-bit number, I need a small multiple of n quantum bits. So for an RSA factoring number of 2048-bit RSA, I need probably on the order of 2 to 3 to 4n quantum bits. And we can come up with very precise measure of that, but the number of, and if I double the number of bits in the key, I only double the number of quantum bits I need. So once I can manufacture quantum computers in any reasonable size, there's no exponential growth to help protect me from a defensive practice. These problems all of a sudden become solvable much more quickly. And whether I'm talking about a quantum computer that runs at a megahertz or a gigahertz doesn't change that attack growth, okay? I don't get the benefits anymore. And I've talked about RSA, but this is actually a problem for every algorithm that we use today, say in TLS, to some degree or another. If we look at, if you're making an HTTPS connection today to a reasonably recent server with a reasonably recent browser, I've always had to train myself to use reasonably recent because someone out there is still running Windows XP. You're going to use a combination of elliptic curve Diffie-Hellman for key agreement. You're going to use RSA probably to evaluate to authenticate the server. You're going to negotiate a session key. You're going to feed that into AES. You're going to use it with a new hash function like SHA-2. And all of those can be attacked to some degree more efficiently with a quantum computer. The number theoretic algorithms, the public key algorithms, fail catastrophically if I've got a big enough quantum computer available. That's true for factoring underlying RSA. It's true for elliptic curve discrete log problems underlying ECDSA and ECDH. Against the metrics, Grover's algorithm lets you do what's called a square root attack, where if it takes you 2 to the 128 time to brute force a 128-bit RSA key, if you got a quantum computer, it's only 2 to the 64 time. So the answer for symmetrics is to double the key lengths, and that actually brings you back into this realm. But for the number theoretic stuff on the left-hand side, none of that helps. So we need new algorithms. Now you're sitting there thinking, well, how real are these quantum computers? Okay, so here's a picture of a qubit, or at least they're trying to find a qubit, and I love to use the physicists' pictures of their labs because cryptographers don't have anything that looks cool for us to show. This is a photo of Charlie Marcus's lab. Charlie is at University of Copenhagen. He's one of the collaborators that works with one of our academic partners that works with the quantum computing team at Microsoft Research. And they are trying to develop something that's called a topological quantum bit or a topological qubit based on these things called Majorana particles. Please don't ask me any more than that. I didn't get past my second semester of physics as an undergraduate, and so my knowledge of quantum physics is limited. I don't have a pointer here. The big cylinder on the left is a dilution refrigerator. That's actually at the bottom of it is where they end up doing all of the trying to run and create quantum bits, and that runs at a small number of millikelvin, so colder than deep space. And then as you go up the stack, it gets a little bit warmer, so there's like a 4 Kelvin layer where they try to do an interface, and then it gets kind of warmer as you go up. Now that doesn't really scale very well, okay? If I need like 8,000 of those to go after RSA, okay, that doesn't look like it necessarily scales, but if I can actually get a lot of quantum bits onto a piece of silicon or some other substrate that goes down in the cold area, and I can figure out how to get the data in and out of the super cold area, then all of a sudden that becomes interesting. So why should we care now? We don't have machines now. We don't have them, but they might in, let's say, 15 years. If you ask the physicists, when are you going to go see a quantum computer come? I was at another talk with our quantum architecture team, and some of the folks there were saying 10 years. I really hope it's more 15 than 10, but because it just gives us more time to migrate the internet, because that's kind of what we're talking about here. But let's say that there is there's a possibility that some well-funded folks will have a quantum computer of what we call cryptographically relevant size in 15 years, or maybe sooner, depending on how much money they throw at it. How long does it take to migrate the internet to a new set of public key algorithms? We've seen how long it takes us just to get off MD5 and get onto SHA-1. That wasn't very good. And we're still trying to get off SHA-1 to SHA-2. And by the way, occasionally I still have a team come in and ask me at Microsoft if they could use MD5. So how easy or difficult is it going to be to get us off of RSA and elliptic curve and onto something new when we don't even know what that something new is yet? The other thing to worry about is communications that have a security lifetime horizon of more than, say, 20 years. That is data that you are sending encrypted today, which could be reasonably assumed to be intercepted and recorded in encrypted form by an attacker and saved for decryption later. If you're talking about national security level information, that stuff's all 30 years or more, and we have to assume that a well-funded adversary would record whatever they get their hands on, save that data, and potentially break it down the road. So we have to start planning to take defensive steps even before a quantum computer becomes built. Third, from a corporate perspective, if my customers start to believe that one or more adversaries they worry about might have a quantum computer, then the problem is real even if the computers don't exist yet. Because my customers want me to have defensive mechanisms in place for them to protect against that risk. So there's a risk management aspect to it. Now add into all of this the US National Security Agency, the NSA, which about 10, I guess 12 years ago, announced Suite B. This was the migration from RSA to elliptic curve-based public key algorithms when they started having all of us add Suite B cryptography into our software stacks. In August of 2015, a week before the annual US Crypto Conference in the US, and without any sort of advance notice, NSA sort of put an update on their website. This is how we make big, broad announcements in fundamental crypto policy. We change a web page. And they started talking about quantum-resistant cryptography. And in particular, they said, for partners and vendors that have not yet made the transition to Suite B elliptic curve, we recommend not making a significant expenditure to do so, but waiting around for the upcoming quantum-resistant algorithm transition, which kind of stopped everybody from doing elliptic curve work until we pointed out that we don't actually know when the quantum resistant stuff's going to come around yet, and maybe you should have people finished. And NSA put out a FAQ, because that's the other way you issue crypto policy, is you put a FAQ out. And they said, we're gonna actually update, and you should continue if you started. But what they were worried about was a real problem, which is if you're starting a procurement process that is going to be a decade long, like you're designing a new class of ship for the Navy, and you don't want to spend all your effort designing and starting that process on the basis of what you think is relevant today versus what you think is going to be relevant 10 years from now. So there is a method there too. And then one final issue about terminology. I use the terms post-quantum or quantum-resistant. You'll also hear people talk about quantum-safe algorithms, all basically the same thing. We're all talking about classical algorithms that are based on other, say, number theoretic problems or other problems where you assume the attacker has a pile of classical computers available to them and a quantum computer, and the access to the quantum computer doesn't give the attacker any significant advantage over having a pile of classical computing. We have to talk about the strength of algorithms in terms of classical attacks and quantum attacks, but it's algorithms where having access to a quantum computer doesn't let your attacker fundamentally break the algorithm, as opposed to what happens with the RSA and elliptic curve today. This is distinct from what you will see with quantum cryptography, which is really about something called quantum key distribution, where if I've got two endpoints and I can, say, shoot lasers between them over some fiber optic line, I can entangle particles and move an entangled particle from one end to the other, and if someone intercepts that, it changes the information that's been transmitted. The Chinese government's been pushing that type of work a lot. You might have noticed some news reports recently about satellites that were doing quantum crypto where they were beaming entangled particles to two stations 1,200 kilometers away, completely separate and not related to what we're talking about here. Quantum key distribution is nice if you've got the physical plant for it that doesn't scale to the internet. I need something that I can install on every laptop in this room that's going to give me a defense against, a potential quantum computer coming. So let's say that I get a quantum computer in 2030. I started this project at Microsoft in 2015. We had done a little bit of work on it in 2014. And at that point, everyone said, maybe we'll get something reasonable sized in 2030. There's, say, there's a non-zero but greater than epsilon chance of a big quantum computer coming along by then. You start working backwards from 2030 as to how long it takes to do things like research and design new algorithms and prototype and standardize and roll them out and update all the protocols and update your software stacks and get your customers to take the updates and then turn off the old stuff, and you realize 15 years is not enough time, or it's right on the edge, which is why we and everybody else in the industry are worried about this problem now, because when you work backwards from 2030, we're actually started this whole effort a little bit late. But we're working on it right now, and I've noted where we are in terms of the process on the timeline, and we and everyone else are in the process of developing and submitting for standardization consideration new quantum resistant public key algorithms. And the double question mark up there is 10 minutes, okay, 5 years out, and then the single question mark is 10 years out. And if I get a quantum computer in 10 years, we'll be most of the way deployed. If I get one in 5 years, we're not going to be kind of far enough. And what's driving sort of the work here, and you'll hear Donna Dodson talk about this in the next talk a little bit as part of her broader talk, is the NIST post-quantum competition timeline, which is the US government has started the process, they don't like to call it competition, it's a selection process officially, to standardize one or more new public key algorithms that are quantum resistant. And the proposals are all due into NIST by the end of November, and that will kick off a 6-year standardization process where we will see a series of workshops, and the cryptographic community will attack each other's proposals, and just like was done with AES and with SHA-3, the end result of that will be a number of algorithms that will become standardized for the US and then hopefully to go on to international standardization that will eventually replace RSA and elliptic curve. Now, okay, I've got less than 10 minutes. Let me tell you a little bit just about some of the schemes that we're working on, because my team at Microsoft is part of 3 proposals that are going into NIST, 2 key encipherment schemes and 1 digital signature scheme. I will not go into the math here. It's after lunch. But I at least want to give you kind of a flavor for the types of problems we're looking at. When you look at the families of post-quantum, there's been a lot of work on quantum-resistant algorithms, and they tend to break down into based on 5 different fundamental families of number theoretic algorithms. Those based on coding theory, those based on lattices, cryptographic hash-based signature schemes, those based on isogenies, which are maps between elliptic curves, and some multivariate schemes. My team's part of 3 proposals, 1 lattice, 1 isogeny, and then 1 that's actually not based on a number theoretic scheme, but on doing simulated multi-party computation proofs of knowledge. For all of these, the process of coming up with an algorithm is actually pretty tough, because you start with what you think is a hard problem. You actually have to build a crypto system out of it. That's not necessarily the easiest thing to do. You have to then try to attack it yourself and improve the best classical and quantum attacks. You then have to size it based on the security level that you want to provide in terms of defense, because there are engineering trade-offs between how much bandwidth, what are the key sizes, what's the performance of these algorithms. You have to develop fast and secure implementations that don't have side channel leaks and things like that, such as some of the ones that we heard about classically earlier this week, if you were paying attention to some of those attacks. And then you have to integrate them into the existing infrastructure and show that these algorithms actually work with all of the common protocols that we use today. So that takes some time. So here are the 3 that you might hear about a little bit down the road if you kind of watch this that my team is part of. One of these is called Frodo, and it's based on the lattice problem or learning with errors, and it's a key encipherment scheme. The other one's called Psych. It's a super singular isogeny key encipherment, and the third one we call Picnic for a post-quantum non-interactive zero-knowledge key agreement scheme. PQNIZK came down to Picnic. That's how we came up with that. I just want to show you who's collaborating with us. These are all multi-industry team collaborations. This is not a one company comes up with sort of thing. You want lots of partners. You want to collaborate on this, and these are industry and academic partnerships. All of the ones that we are involved in are. The first one is Frodo. This is a collaboration between us and researchers at Google, folks at NXP, and then at CWI McMaster and Stanford. So it's an international collaboration. It is a lattice-based scheme. This is sort of the family that's the greatest. Now, why do we call it Frodo? Because we previously did a scheme based on the ring learning with errors problem, where you have an algebraic ring structure inside. It's faster with the ring, but it adds more algebraic structure. And from a cryptanalysis perspective, we don't like things with structure, so we decided to get rid of the ring. And thus we got Frodo, and nobody's laughing, and that's humor for cryptographers, okay? So that's why we call it Frodo. Frodo's very efficient. I'll show you some numbers in a little bit, but it's got relatively large keys. And for all of these schemes, none of them are drop-in replacements for the cryptographic schemes that we're dealing with today. They all either have larger keys, or take more bandwidth, or they are slower, or et cetera, or a combination. The super singular isogeny work, I see I got a little typo on the slide. It's Microsoft, Amazon, and then 3 universities, Waterloo in Canada, Versailles and Radboud in Europe. And again, this is an elliptic curve-based scheme based on these isogeny maps between curves. Nice small keys, relatively slow. Just to give you some idea for the performance metrics, here are the latest numbers for implementations, which, by the way, are up on GitHub or will be as soon as things go into NIST. We have prior work that's already up there. Targeted to the first security level that NIST asked us to go after, was called level 1. Compared to, say, RSA 3072, the elliptic curve, Diffie-Hellman using the NIST P256 curve, and New Hope, which was prior work based on our, it's not our work, but it's based on our prior ring learning with error work, and that's sort of the fastest ring structure. And the times are, Frodo is comparable to the time on elliptic curve, but it sends a lot more communication between Alice and Bob. The key sizes there are about 11 kilobytes, 12 kilobytes, as opposed to a small number, 2048 or 4096 bits. For SIDH, or Psych as we now have to call it, our time is down to it's about 10 times slower, but we send a lot less bytes across in terms of communication. These are some of the engineering trade-offs you have to worry about. For our signature scheme, where the signature sizes I'll show you in a minute, that's another collaboration between us and 4 academic partners. And it basically does not have a number theory problem at the base of it, but it's just based on the difficulty of hash collisions or doing pre-image attacks on hashes. Small keys, but really large signatures, to give you a feel for that. Signature size on a typical Picnic install is about 120 kilobytes. So I point this out because if you think about migrating any of your existing systems, like smart cards, certificates, PKI, things like that, don't assume that the new algorithms are going to have the same engineering characteristics as what you're doing today. Yes, we have made X509 certificates using Picnic signatures and run that through TLS, through OpenSSL. Works fine, but not all software maybe has that flexibility, and that's kind of one of the important things to think about. So in a couple minutes, since I've got a couple minutes left, let me talk about where I think things go from here. First off, everybody starts with OpenSSL when they look to do an integration. Okay, that's the #1 thing people go do, and you can go find lots of examples of post-quantum schemes, ours included, integrated into OpenSSL. And it works. And if you told me I had to deploy something absolutely today, I could pull one of our algorithms off the shelf and we could show you an integration with OpenSSL for protecting TLS, working just like it does today, negotiating on both ends, and at most you take an overall factor of 2 hit in terms of throughput. Okay, so there are engineering options available today. Now, we don't really know enough about any of these single algorithms yet, so I would not recommend solely depending on them, but using them in a hybrid mode where you do an existing classical scheme and mix it with a post-quantum scheme. And in fact, any of these Lines over here where you show an algorithm plus ECDHE is exactly that. We have basically done 2 key agreements in parallel, derived 2 keys, mixed them together to get a content key, and that gives you the belt and suspenders support. Sort of to give you protection against a quantum scheme not having the same classical, because that just hasn't been studied long enough. So beyond TLS, beyond OpenSSL, what do you go do? Well, first off, one of our collaborators, Doug Stabile at McMaster, has developed something called OQS, or the Open Quantum Safe Library, which is basically a common API for plugging crypto algorithm for post-quantum algorithms into. If you wanted to go do an integration today, I would recommend that what you do is integrate OQS into your software stack, and then you get the benefit of lots of other algorithms that have already been plugged into OQS, and then you can mix and match and try different things out. And we've done this with ours, and there is an OQS-enabled OpenSSL. There's an OQS-enabled OpenSSH that we did. There's more that's coming down the pike in terms of other protocols. And then in my last minute, let me just leave you with some closing thoughts. Quantum computers are coming, maybe not for a decade or more, maybe sooner than that if we're unlucky, but within the protection lifetime of a lot of the information we deal with today. So if you haven't already, please start planning for that transition. Okay, and the best thing that when I have industries, customers come into Microsoft and they say, well, what should we do? I said, the most important thing you can do right now is plan for cryptographic agility. Make sure that the systems that you are designing, architecting, specifying for procurement and buying from whomever your vendors are, have a plan. Make sure they've got a plan and that they have engineered their systems to be flexible and can adopt other sorts of algorithms. Practical engineering exists today to deploy PQ, but really we're still at the beginning of understanding and attacking these algorithms. There's been some, but that's part of what's going to come out of the NIST process. And then finally, what I suspect will likely happen early on is people, when they start saying, oh, gee, we forgot to plan, and we better do something really quick, is they'll start wrapping post-quantum VPNs around all their existing links. So if you have a big infrastructure right now, that's where I would kind of think about doing, and there's options there. I will end with just saying, I don't know if the slides are going to be made available, but all of this is available open source. All of our implementations are up on either microsoft.com/research, or we've been migrating everything to GitHub. So you can download stuff from there, learn more about this project. I'm happy to talk about it further, but I believe I've hit my 30 minutes. So thank you very much.
We've got time for a couple of questions. Do we have another mic? Yeah.
First, a request. Please put back the previous slide with
Absolutely.
all the
Sure.
URLs. Okay. Question is, you gave some kind of comparative measures, billion years versus...
In terms of CPU years, in terms of factoring, yeah.
A few hundred seconds.
Yeah, that's right.
For quantum key. Is there, or can you give one or two examples, non-trivial examples, where one can really compare the application of the classical schemes with the quantum schemes? For example, is there an NP-hard problem for which you have made an estimate?
I'm sorry, so you want to know if there's, so we don't, both, so factoring's NP-hard.
Yeah, please give one or two examples of a problem where you have derived a measure for how long the quantum scheme would take as compared to the classical scheme.
Okay, so you want some examples of exactly how long it would take you to do it. So there's actually a paper that's coming out either at CCS or AsiaCrypt, where we have more precise counts of the total number of quantum gates that you would need to go after elliptic curve problems. And I can get you a preprint or something of that if that's what you're looking for. Or are you looking for problems outside of the number theory space? I'm
trying to find out if realistic estimates have been made.
Yeah, so those are realistic estimates in terms of how long it will take to factor based on how many quantum gates that you'd have to go construct. And probably the best thing for me to do is actually get you a copy of the paper that gives you more precise gate counts and estimates on that. Okay? I'd be happy to do that. You just kind of see me afterwards or during the break.
One more question? I'll sneak in then. How do you think the internet infrastructure is going to change? What are going to be the second order effects of moving to post-quantum crypto?
So A, it's going to take a lot longer. We're going to find a lot more stuff breaks. So that's the first order effect. What I think you'll start to see, and Donna over here is going to talk a little bit, as I said, NIST has this 6-year process. Some folks in the industry may not wait for that, and we might start to see proposals quicker. I think the second order effects are going to come by, as I said, we're going to have larger signatures and larger amounts of information moving around and increased bandwidth. And it's not clear we've planned for that in a lot of the middle boxes and things like that. That all of a sudden, if you assume that you need to pass 12 kilobytes of key material instead of 32 bytes of key material, and you've got hard-coded limits in a lot of the middleware boxes, stuff's going to break. And I think that we kind of found this when we tried to upgrade from MD5 to SHA-1. Everyone got surprised by the MD5 break, and it launched, certainly inside of Microsoft, a huge effort to find all the places where it turned out we had, 50 some odd implementations of MD5 inside of Windows. I think the second order effects you're going to see are, it's going to be a long transition. You're going to see stuff that breaks. You're going to see a lot of keeping back compat around a lot longer than you would like, and worries about, hard-coded assumptions that got made in protocol stacks that no one's touched for a long time. So that's why we should all start looking at it now.
Thank Brian one more time.